Hi, thank you so much for joining me. In this example with limiting reactants, we're going to merge the concept of molarity and limiting reactants into one problem. And we're going to use what I call a BSA table, before, shift, and after. Sometimes you'll see that as a C for some teachers, before change and after. We can do molarity with this if we've accounted for all dilutions. You can use pressure of a gas if volumes and temperature are the same throughout. You can use volumes of a gas if pressure and temperature are the same throughout. In this example, we're going to do moles, probably the most straightforward of the type of examples. And so the first step we need to do is find our before moles. And it's handy to bear in mind that volume times molarity is equal to moles. So I like to say you voom to moles. I use volume 1 molarity 1 equals volume 2 molarity 2 for dilution, and I call that voom voom. And so we're going to voom to mole. But the key is you have to have liters. So we have to convert these to liters. So I'm just going to work that first one for us, 0.025 liters times 0.5 molar, and that gives us 0.0125 moles. And I would do this similar for NaOCl, 0.075 times 0.5, and you should get 0.0375, and for NaOH, 0.025. And then none of this and none of that, and honestly, in an aqueous solution, we won't typically care about the water that's produced in this situation. So now we have moles. The trickiest part to this type of a problem is to determine the limiting reactant. And to do that, we need to compare what we have to what we need. So our before moles are what we have available. The 1 to 4 to 2 ratio is what we need. So to determine that, we're going to do an evaluation. And I like to just write that number on top so it doesn't get mixed up with our work towards our answer. So we're going to take what we have and we're going to compare it to what we need. So for this, it's just 0.0125 divided by 1. So we're dividing by the balancing coefficient, and I get 0.0125. For NaOCl, it'd be 0.0375 divided by 4, what we have compared to what we need. And we get 0.009375. And if we did NaOH the same way, 0.025 divided by 2, you get 0.0125. Now, the limiting is the smallest of these evaluation numbers. And so in our case, that means our sodium hypochlorite is our limiting reactant. Now, once you're done with those, I urge you to just cross them out. If you're honors, you'll never use them again. If you're AP and IB, that's actually an important value. That's our moles of reaction. And you might see that pop up again when we do thermodynamics and thermochemistry. But for now, we're going to ignore it. Once we've done our evaluation, we don't need those values anymore. So we now know what our limiting is. A reaction proceeds 100% to product until our limiting runs out. So we're going to lose all of that limiting. So we know our first question here. What is the limiting reactant? We know our second, what are our excess, our NaOH and our Na2S2O3 are our limiting reagents. So everything arises from or proceeds from our limiting. They all depend on that. I'm putting negatives here because we lose reactant. And I'm going to put positives because we gain product. Now, if you remember your other stoichiometry, you likely did dimensional analysis, you may have done proportionalities, you would know that we can't stop here. We have to multiply this by the mole ratio. When we go from one substance, in this case, to our limiting, so this will be our from, we have to do a mole ratio. And it's always where you're going to divided by where you're coming from. So there's an implied 1 there. So it's 1 over our limiting coefficient. This is sodium hydroxide's 2 over our limiting. Just make sure you put the limiting in the denominator every time. Sorry, that's 2 over 4. Can't quite see that one. And then we have 4 over 4. Okay, so we need to multiply each of these by our limiting reagent. Let me try to clean that up. 2 over 4. Okay, so we multiply by our mole ratio. You know what? This is the hardest part. If you can get to this part, everything is downhill in terms of difficulty from here on in. So what we do is we add up all this BS. B plus S equals A. And that's going to give us our aftermoles. After the reaction has proceeded to make the maximum amount of product possible, this is what's going to be left over. And I think this is the big win, because at this point, how we get our excess remaining is much more intuitive than what many people teach, and frankly what I taught for many years as well. I taught more of a memorized algorithmic way, and I think this is a little bit clearer, logical way. What did you start with? How much did you use? The rest is left over. Okay, and 0.375. So those are our after moles. Once you know moles, once you know this after stage, most of the questions you can be asked are pretty trivial. If it was gases, you might be asked for pressures. You know, moles and volume temperature, you can get pressures. In this case, we're going to do molarity. We could do mass. Mass to moles use molar mass. But this question is all about molarities. So we are now going to calculate our molarity. So they said, what is the excess reactant after the reaction is complete? So to do that, we've now mixed all of these solutions together. Our 3 solutions were mixed together. So we have a total volume of 0.150 liters. 150 milliliters or 0.150 liters. So my molarity of Na2S2O3 is equal to its moles, 0.03125, over the volume. So that's pretty much all there is to it. All of these are simply taking moles over volume. For my sodium hydroxide, I have 0.06625 moles over 0.150 liters. And then the question asks us, what is the maximum molarity, the theoretical yield of sodium sulfate? Could have asked sodium chloride, the question just didn't. And so to find those moles, we have molarity. We take those moles and put them over our same volume. That's our total volume of solution. Okay? At the AP and IB level, we will always assume when we mix volumes that the total volume is the sum of the individual volumes. And that's what we did here. And so I have those answers. You should be checking my work for those. I get 0.0208. Always double check your math on that. For NaOH, I have 0.44 molar. And for my sodium sulfate, I have 0.125 molar. So that's a pretty involved limiting reagent problem, like the AP and IB level, but I think a very good challenge for honors and pre-AP as well. Hope this cleared some tough issues up on how to do limiting reagents. Thanks for joining me.